In this video, we're going to derive the sine of x plus y. And what that pretty much means is it's pretty much taking the sine of two angles that are added together. Okay, so the sine of the sum of two angles, basically. And what I'm going to do is, and since we're representing these as angles, I'm not going to use x and y. I'm going to write it as alpha and beta, because alpha and beta are Greek letters, and we know Greek letters tend to be used for angles, like theta, but in this case we're using alpha plus beta. Okay, just to be consistent. Okay, so in order to derive this, in order to figure out what the sine of alpha plus beta is, we're going to need to do something in order to figure that out, obviously. So what we could do is we could draw a diagram. In this case, we're going to pretty much draw those two angles, right? Those two arbitrary angles. So we're going to say that we have this triangle right here, and this triangle has an angle alpha right there. So this angle right there, that angle's alpha, and it's associated with this right triangle. Now, since we're adding these two angles, I'm going to have to draw angle beta above angle alpha. It's going to look something like this. Okay? I'm going to need to extend this a little bit. Wait, no, never mind. I'm actually trying to draw the triangles in a certain way so that we can get the best possible way to derive the sine of alpha plus beta with this sort of method, right? So this is beta, right? And I've purposefully drawn this line right here so that if you were to do this, you draw a vertical line like this, it'll intersect with this vertical line, part of this right triangle. Right? I did that on purpose, right? And you'll see why. It's pretty easy to tell why. But pretty much, since I'm trying to draw a triangle associated with beta, it has to be a right triangle, right? In order to do trigonometry, right? So I'm gonna have to extend this line a little bit and bring that line down, so that'll be a right triangle associated with beta. Now, the reason why I drew this point purposefully so that we can make a vertical line like this, right? So this is a vertical line, obviously, it has to be because that's what we did, is because we also needed a triangle for the angle alpha plus beta, right? So we could associate this triangle with alpha plus beta. And that's pretty much it. Now, let's see what we're dealing with. So the triangle we did for alpha is this right triangle right here. The triangle that we did for beta is this right triangle right here. And the triangle we did for alpha plus beta is this triangle right here. All right, so that's what we've done. Now, but it turns out there's actually another right triangle here that we haven't really thought about. We haven't really said anything. It's right here. It's another right triangle, as you can see. And notice how this triangle and this triangle are similar to each other, right? We have congruent angles right here. So these two angles are congruent, and these two angles are congruent because they're right angles. So this triangle has to be similar to this triangle. So since this angle is congruent, these angles are congruent, that means these angles have to be congruent. So this angle right here has to be angle alpha, right? So alpha and alpha. So this right triangle is also associated with alpha. So that's probably going to be important later when we're trying to derive sine of alpha plus beta. But how do we even start by deriving sine of alpha plus beta? Well, we know what this means because we know that sine of an angle is opposite over hypotenuse for a right triangle. So for a right triangle, in this case, what that means is sine of alpha plus beta is going to equal opposite over hypotenuse. But we haven't labeled any of the sides yet, so I guess that's what we should do that, right? We should label the sides because that would make sense. And I'm going to label them red. So I'm going to say that this side length is A. I'll call this side length B, side length C, side length D, E, F, and I'll call this G and H. Right, just to label them in that sort of way, okay? So, oh wait, I don't need to label the H. I totally forgot. Okay, so that pretty much these 7 side lengths that we have right here labeled. And because now that we have labeled them, we are now able to write what sine of alpha plus beta is. And so what would sine of alpha plus beta be? It would be pretty much focusing on this right triangle because it's associated with alpha plus beta. It's going to be opposite over hypotenuse. So C plus D over A. So we get C plus D over A. Now, when we're deriving sine of alpha plus beta, we don't want our answer in terms of these side lengths because we're just using these side lengths to help us derive sine of alpha plus beta. So we'll have to get these to cancel out eventually and make sure everything is in terms of alpha and beta. Okay, that's what we need to do. So what we could do is we could find what C is in terms of A, and we could find what D is in terms of A, and get A to cancel out and be left with alpha and beta, pretty much trigonometry functions like sine and cosine in terms of alpha and beta. So we got to find what C is in terms of A and D is in terms of A. So that's what we're going to do. So first thing we're going to do is find C in terms of A. Okay, so that's what we're going to do. So to find C in terms of A, when we're doing that, we cannot use the same right triangle that we already used, or else it's just not going to help us. We got to use other right triangles. And the right triangle that we could use is, notice how C is a part of this right triangle right here, right? And we know that this triangle is associated with alpha. So we could write what C is in terms of B, and then find what B is in terms of A because of this right triangle right here, right? We could relate C to B with this triangle, and then we could relate what B is to A using this triangle. And that'll work. So to find C in terms of B, we got to use this triangle, which involves alpha. Relative to alpha, B is the opposite, B is the adjacent, C is the hypotenuse. So we're going to use cosine. So the cosine of alpha is adjacent over hypotenuse, right? So that's what we have for cosine of alpha, right? Remember, we're finding C, so we're going to solve for C. We get C is equal to B over the cosine of alpha. So that is what C is, pretty much. That is what C is. So now that we have that, we got to find what B is in terms of A. And we can use this right triangle right here. And this right triangle relates to beta. Relative to beta, B is the opposite, A is the hypotenuse. So we're going to use sine. So pretty much the sine of beta is equal to opposite over hypotenuse. So we get B over A. B over A, which means that B, if you solve for B, it's going to be equal A sine of beta. So all we got to do is put B into there, right? And that's pretty much it. C equals A sine of beta divided by the cosine of alpha. So as you can see, we have found what C is in terms of A. So that is what C is in terms of A, and that's what we're going to put into that equation eventually, right? So now that we've found that, I think it's important that we write that down. So we have found what C is in terms of A. So C is equal to A sine of beta divided by the cosine of alpha, right? This is going to be useful later on. So all we have to do now is find what D is in terms of A, and then we can figure this out. So instead of finding C in terms of A, we're going to find D in terms of A. Not as simple as finding C in terms of A, though. It turns out finding D is actually a lot harder. All we had to do for C is we just had to relate C to B and then relate B to A. Pretty simple. But what do we do for D? Well, if we relate D to G, what happens? The only triangle we could use is we could relate D to G, then G to A, but that would involve using this triangle, the triangle of alpha plus beta. And we don't want to reuse this triangle. It won't help us. We want to use other triangles. So if we can't really relate D to G, turns out the only option we have is relate D to E, right? We can't relate D to G to E. That doesn't make sense. It's the same triangle. If we relate D to E, then let's just see what happens, okay? So to relate D to E, we use this triangle right here, which is alpha, and D is the opposite, E is the hypotenuse, so we do sine of alpha is equal to opposite over hypotenuse. Solve for D, because remember we're finding D. Solving for D, we get E sine of alpha. Okay, so now that we found D in terms of E, we gotta find what E is in terms of A. But there isn't any right triangle that directly relates E to A, right? The only triangle we really got is this triangle right here, right? Which we're not gonna use that triangle. We're only gonna use right triangles. Now, E is not related directly to any right triangle. It's not directly related to any right triangle, but it is related to two side lengths that are related to right triangles. Check this out. This is going to be really cool. So right here, we're solving, remember, got to find what E is, okay? It turns out that we could say that E is equal to E plus F minus F. You just got to appreciate how cool this is, because nobody really thinks about adding F then subtracting F. But it turns out we have a line E plus F and a line F here, because this is line E plus F and this is line F. So we have those two side lengths, and E plus F is related to a right triangle. It's related to this right triangle right here. So that works out really nicely. And also, F is also related to a right triangle. F is related to this right triangle that we have right here. So we could relate E plus F directly to A, right? E plus F could directly be related to A because we have that right triangle. Well, F could be related to B, which we know we can relate B to A. And that's all we have to do. So in order to find what E is, we got to find E plus F in terms of A and F in terms of A. So for E plus F, all right, we're gonna find E plus F in terms of A, then F in terms of A. So starting with E plus F, we're using this right triangle right here, right? It involves beta, and pretty much we have E plus F as the adjacent and A as the hypotenuse. So cosine of beta is what we're gonna be using. So the cosine of beta is E plus F over A. So now that we know that, we solve for E plus F. And that is it. We have found E plus F in terms of A. That's pretty much all we had to do. So now that we found that, I'm just gonna circle that because it's gonna be useful. Now we're gonna find F in terms of A. Slightly weird, slightly more complicated, but we kind of already done something like this. It's kind of like finding C to B to A. In this case, we're just going F to B to A. Now F and B are related by this right triangle, which involves alpha relative to alpha. F is the opposite, B is the adjacent. So we're using tangent, okay? So I'm gonna write right here, the tangent of alpha, opposite over adjacent, so it's F over B. Okay, that's pretty much what that is. And now that we have that, F over B, we gotta solve for F because we gotta find what F is. F equals B tangent alpha. I know the writing is a little small now, but anyways, we gotta find what B is in terms of A. And I think we already did this, I just erased it, didn't I? Pretty much the sine of beta is B over A. So sine of beta equals B over A. We kind of already did this, I just erased it earlier. B is equal to A sine of beta, okay? So this will go there, and yeah. So knowing this, pretty much I need to substitute that in. So F is equal to A sine of beta times the tangent of alpha. So now we have found F in terms of A. So we have found this and this in terms of A. We take this, subtract that, we get E. Substitute E back into what we know about D. We have D in terms of A. So we just gotta kind of clean this up. I'm not sure if I have enough room, so I got a little bit of room. I got room on the bottom. So I guess let's just move to the bottom over here and try and work with that. So we got to find what E is. So over here, I'm going to find what E is. So to find E, all right, it's going to be E plus F. So A cosine beta, minus F, which is A sine beta tan alpha, A sine beta tan alpha, right? So that is what E is in terms of A. We take whatever E is and put it into this equation right here, which is for the equation for D. And pretty much to do that, you're pretty much taking E and multiplying it by the sine of alpha. So, just to simplify this is E, right? We already know that this is E. If we multiply this by the sine of alpha, we get D. This is D. So as a result, this is D in terms of A. We found it. There it is. So yeah, this is D in terms of A. I'll just quickly circle it. And there it is. That's pretty much it. So we found C in terms of A and D in terms of A. I'm thinking I'm just going to circle these two because that's what we got to bring most attention to. This stuff, pretty much we have found C and D in terms of A, so I don't need this stuff anymore. All right? This work that we just did was just to find D in terms of A. So now that we have found C and D in terms of A, we can go ahead and substitute C and D back into this equation. So back into this equation, and A will cancel out, and we're left with stuff like cosine of beta, sine of beta, cosine of, all that trigonometric stuff. And once we simplify that, we'll have the sine of alpha plus beta. And so that's all we really had to do. And yeah, we're just going to substitute in this stuff into here. I'm going to use a different marker because this one's kind of dying. Okay, so the sine of alpha plus beta is equal to, okay, that's fine. C, oh wait, we're going to need to erase this again because this is a fraction. It's going to require more room to fit that. So let's see if, I think we'll fit it. Yeah, I think we'll fit it. The sine of alpha plus beta is equal to, I think you guys can see up to about there. Maybe a little bit further, but okay. A sine of beta divided by the cosine of alpha. You take this and you add D, which is this stuff. So you're adding the sine of alpha. Right, you're multiplying that by whatever's in this parentheses. I'll just write all that in there. We will fit it perfectly. Not perfectly, but yeah. We have pretty much C plus D in terms of A divided by A, right? Because of how cancellation works with division, we already know if we were to like, pretty much, we already understand how cancellation works. A cancels out. Oh man, all my markers are dying. Okay, we have pretty much just done that. As a result of that, I'm just gonna rewrite what we have. And so this will be a little bit cleaner because we have no more, well, we do have a fraction there, but we don't have this large fraction anymore. Okay, sine of beta time all over the cosine of alpha, and we'll just, yeah, I'll rewrite all this. Yeah, I'm just gonna rewrite it all. I'm not gonna do any more steps right now. Okay, so that's what we have. We're just gonna simplify this now. That's all we have to do. Now, how can we simplify this? Well, I'm thinking the best way to do it is to expand sine of alpha first. Okay, so when we expand it, sine of alpha cosine beta, and then minus, now, all right, so what we're gonna do is we're gonna group up sine of alpha and tan of alpha because when you multiply these two things together, they kind of go with each other. So what I'm gonna do is, I'm actually going to write it this way, all right? So let's just kind of think about what's going on here, all right? Sine of beta, sine of alpha, tan alpha, all right? I'm going to write tan of alpha as the sine of alpha all over the cosine of alpha. And when you multiply sine of alpha times the sine of alpha, it's the sine squared of alpha, right? So this divided by the cosine of alpha. Okay, I'm just rewriting it so feel good about that. This is cosine alpha, my bad. So pretty much the result of this comes from sine of alpha times sine of beta times the tangent of alpha. And of course, you're subtracting it. All right, that's pretty much it. Now, there's something else that's pretty interesting about this. We could group the first and last term together. All right, so check out what happens when I do that. All right, I'm just going to group those together. So I'm going to write this term first. Sine of alpha, cosine of beta. I'm going to group these terms together. So we get the sine of beta all over the cosine of alpha minus, now check this out. We could write this as sine of beta over the cosine of alpha times the sine squared of alpha. So notice what happens with these two terms right here. You can factor out the sine of beta all over the cosine of alpha. And you're left with, remember, when you factor this out, you're going to be left with 1 minus the sine squared of alpha. We have a trig identity here. I'm pretty sure you guys can see this, right? Yes, you can. Okay, this is the cosine squared of alpha, because that's just our trig identity. It's sine squared plus cosine squared equals 1. We could write that as the cosine squared of alpha. When you do cosine squared of alpha divided by alpha, that's just cosine of alpha. So we could just do that, get rid of that, and yeah, it's pretty much, that's all that is. So it's sine of beta times the cosine of alpha. Or, yeah. That's what happens when we simplify that. That's pretty much it. That's what happens when we simplify that. So we could actually do this. We could just rewrite it all as this. We can move this up here, and we get plus the sine of beta times the cosine of alpha. That is it. I need no markers. That is it. That right here, this is the sine of alpha plus beta. It's the sine of two angles that are added together. And yeah, that's pretty much where that comes from. And yeah, that's pretty much it. I hope you enjoyed. I thought it was pretty cool. Yeah, it is.